Welcome back, everyone. So today we're tackling basic optics, specifically demystifying astigmatic refractive error. Now, I know for a lot of you, the physics of spherocylindrical lenses can feel, well, incredibly intimidating, right? You look at those complex diagrams and power crosses and think, man, how am I ever going to use this in the actual clinic? But today, we're going to change that. We are going to transform these abstract, kind of dry optical concepts into intuitive, clinical mastery. By the time we wrap up this explainer, you won't just be blindly memorizing equations for your OCAPs or your boards. You're going to understand exactly what's happening to the light as it enters your patient's eye. So let's build that foundation together. Okay, let's dive right into our roadmap for today. We're going to cover 1. The farpoint review, 2. Spherocylindrical lens basics, 3. The refraction of cylinders, 4. Forming the focal lines, and 5. Calculating spherical equivalent. All right, first up, the farpoint review. Let's get anchored in the basics. So you absolutely have to remember this crucial definition. The far point is the point in space conjugate to the retina when the eye is not accommodating. I want to remind you, and I really can't stress this enough, all refractive error is fundamentally a far point problem, period. Think of the far point as the eye's ultimate home base for focus. If you know exactly where home base is, boom, you instantly know the patient's refractive status. Let's look at the eye's intrinsic error lens. For that myopic patient sitting in your exam chair, their far point is just anterior to the cornea. It provides the exact divergence needed to offset the excess convergence of a plus error lens. But for the hyperopic patient, their far point is actually behind the eye, providing the convergence needed to offset a minus error lens. To correct the patient, we literally just place a corrective lens so its secondary focal point perfectly coincides with this far point. It's elegant, it's straightforward, but remember, this math assumes we're dealing with simple, perfectly spherical refractive error. Which brings us to part 2, spherocylindrical lens basics. So what actually happens when the eye isn't a perfect sphere? What happens when the dioptric power is not equal in all meridia? To really get astigmatism, I need you to adopt a totally new mental model right now. If you take a perfectly spherical lens, you can basically think of it as two identical cylindrical lenses just layered right on top of each other, oriented 90 degrees apart. But a spherocylindrical lens, the exact kind we use to correct astigmatism, is fundamentally different. It's composed of two completely different cylinders at 90 degrees. If you can just visualize this lens as two separate overlapping cylinders, I promise you the rest of this whole optical puzzle will just effortlessly fall into place. Moving right along to part 3, the refraction of cylinders. Okay, if our astigmatic lens is really made of two different cylinders, we've got to first isolate exactly how a single cylindrical lens behaves when it encounters parallel rays of light coming from infinity. Now listen carefully because this is a classic board rule. A cylindrical lens has 0 power in the meridian of its axis. Let me just repeat that because it's a huge OCAP pearl. There is absolutely no vergence added along the axis. None. Because power only exists in one meridian, it is physically impossible for a simple cylinder to focus parallel rays into a single sharp point. No way. It just can't happen. So what does the light actually do? Try to paint this visual picture in your mind. As parallel rays hit the cylinder, they converge in one meridian only. Instead of a cone of light narrowing down to a nice little point, the light sort of stretches out. It forms a series of rectangles. And these rectangles, they vary in width or height as the light travels, eventually culminating not in a point, but in a single crisp focal line. And here's the absolute key orientation you need to lock in. This focal line runs perfectly parallel to the axis of the cylinder, which means, logically, it forms completely perpendicular to the meridian of power. Let's keep building. Part 4, forming the focal lines. Now that we know what a single cylinder does, let's recombine our two different cylinders to see how they actually interact as a true spherocylindrical lens. Imagine you have a patient with a prescription requiring a +1 diopter and a +2 diopter spherocylindrical lens. This example brilliantly illustrates the whole journey of light through an astigmatic lens. The rays are converging in both the vertical and horizontal aspects, but, and here's the kicker, they aren't converging at the same speed. The horizontal rays are passing through the stronger +2 diopter meridian, right? So they converge way faster. Chronologically, as the light travels, the bundle morphs into a vertical oval, then it collapses into a sharp vertical focal line. After that line, those horizontal rays actually start diverging, while the vertical rays keep right on converging, which gives us a horizontal oval, then a perfect circle, and finally a horizontal focal line. Let's pause for some active recall here. Think about the clinical math. The horizontal rays hit that +2 diopter power meridian and converge really rapidly to form that first anterior vertical focal line. So what is the physical distance from the lens to this focal line? Take a second, do the math in your head. Got it? The answer is 0.5 meters. The math here is beautifully simple. The power is +2 diopters, right? To find the focal distance, you just take 1 and divide it by the dioptic power. So 1 divided by 2 equals 0.5 meters. All right, let's prompt that active recall cycle again. The vertical rays are passing through the weaker +1 diopter meridian, which means they're converging much, much slower, eventually forming the posterior horizontal focal line. So what's the distance from the lens to the second focal line? Exactly, it's 1 meter. We validate our thinking with the exact same formula. 1 divided by 1 diopter equals 1 meter. Boom. This marks the exact point in space where the horizontal focal line forms, even as those previously focused horizontal rays are now diverging vertically.
Almost there. Part 5. Calculating spherical equivalent.
Now let's see how all this builds into one of the most critical concepts in ophthalmology. I want to draw your attention back to that mysterious morphing zone right between our two focal lines. That space where the overlapping ovals balance out to become perfectly round. Somewhere during this transition from a vertical oval to a horizontal oval, the beam of light forms a perfect circle. So here's my challenge to you. What is the dioptric power associated with this specific intermediate circular face? The power is plus 1.5 diopters. Clinically, we call this the spherical equivalent. The crucial takeaway here is that the spherical equivalent is, quite simply, the average power of the two cylinder lenses. We just took our plus 1D and our plus 2D, averaged them out, and got plus 1.50D. And this brilliantly illustrates how a spherocylindrical lens focuses light on average. At this specific point, it behaves just like a plus 1.50 spherical lens. Okay, time for the final Socratic math question of this explainer. If the power at this perfect circle is plus 1.50 diopters, what is the exact physical distance from the lens to the circle in space? You apply the exact same fundamental optics rule we've been using. Distance equals 1 divided by the dioptric power. So 1 divided by 1.5 equals 0.67 meters. This calculation firmly locates this circle in physical space, exactly 0.67 meters away from the lens. Let's bring all of these calculations together into one unified framework. Look at how beautifully this maps out. The interior line is driven by the plus 2D power, sitting at 0.5 meters. The posterior line is driven by the plus 1D power, sitting at 1 meter. And right smack in between them, dioptrically speaking, is our circle, driven by the spherical equivalent of plus 1.5D, sitting at 0.67 meters. You can clearly see the exact inverse relationship between the increasing distance and the decreasing power. Now, pay very close attention to this next part, because I am absolutely flagging this as a massive OCOP pearl and a classic board trap. Seriously, write this down in your mental margins right now. The dioptric halfway point is not the same as the geometric halfway point. Think about it. Dioptrically, 1.5D is exactly perfectly halfway between 1D and 2D. But geometrically, look at our distances. 0.67 meters is definitely not halfway between 0.5 meters and 1 meter. The physical geometric midpoint would actually be 0.75 meters. Do not let test writers trick you into confusing dioptric averages with geometric physical distances. It happens all the time. All right, to wrap up this explainer, we can finally definitively answer our initial question. A spherocylindrical lens absolutely does not focus parallel rays into a single point. Instead, it focuses them into a pair of secondary focal lines, which are separated by what we call the circle of least confusion, that perfect circle at the spherical equivalent. But I want to leave you with a provocative thought as we set up our next chapter. Imagine a patient with severe astigmatism is sitting in your exam chair right now, squinting, trying to read the Snellen chart. Which of these three locations, the anterior line, the posterior line, or that circle of least confusion, do you think actually provides them with the absolute best visual acuity? Think on that, and I'll see you in the next explainer.